Welcome back to another Bgcse past paper review. Today we're going to review a physics paper. We're reviewing a paper 3, and this was from the year 2018. Before we start this examination, please remember to write your school number, write a candidate number, write your surname, and also write your initials. Again, please read through the instructions carefully before you start the examination, and also follow all the directives given by the examiner. For the physics paper 3, it is typically for them to provide you with a formula sheet. If you get the formula sheet, please look through it carefully and use the formula where appropriate. Now, for this paper, I am doing section A at this time. If time permits, then I will come back and do section B. Now, let's jump into the first question of section A. And it reads, a worker uses a conveyor belt equipped with motors to move crates from the ground floor to the top floor of a factory. Figure 1.1 shows the conveyor belt in use. Each crate weighs 200 newtons. So I want you to observe the diagram that represents this scenario, and you realize that the height in which from the ground floor to the top floor is 3 meters. The length or distance of a conveyor belt is 7 meters. Okay, again, each crate is 200 newtons. All right, and so let's go into the question now. And the first part of the question, which is part A1, it reads, calculate the work done by a worker lifting 200 Newton crate from the ground floor to the top floor. So if a worker should lift 200 Newton, right? So notice here, a worker is lifting 200 Newtons from the ground floor to the top floor. What this simply means is that the worker is lifting through this vertical distance, or the height of 3 meters. Okay, so once we establish that, now we can go into calculate our work done. Now, what is the formula for work done? Work done is equal to force times distance. The force is the same thing as the weight of the crate. So therefore, we can say right here that the work done in lifting this across the vertical height is 200 newtons multiplied by the vertical height, which is 3 meters. All right, and that equals to 600 joules. So the work done there is 600 joules. All right, just to make a note. So again, the vertical height that we're talking about right here is 3 meters. All right, this is not the work done by the motors, but the work done by a man lifting the weight from the ground floor to the top floor. All right, so let's look at part 2 of this question now. This part reads that the motor works at 110 volts with a current of 0.2 amperes. It takes the motor 1 minute to move each crate to the top floor. So before I go any further, let me just establish this real quick. Now the time here is 60 seconds because it's a minute. Now it asks us now to calculate the electrical energy transferred by the motor in 1 minute. So electrical energy can be approached in different ways. So let's get the first approach I want to look at is that energy of in terms of electrical energy is equal to the current times the voltage times time. Okay. Now, point to note right here, if you should approach it in this sense, that power, right, is equal to current times voltage, right? But also you need to remember, if you're finding energy from power, then you can think about this formula that power is equal to energy over time. Okay, and so if you want to find electrical energy, then it's going to be power times time. So let's make a note right here that the energy from this formula here, energy is equal to power times time. And so therefore, power times time is same as saying IV times T. And that's why I have this formula over this side, because energy is equal to power times time, and power is given as I times V, current times voltage, right? So current times voltage times time is same thing as electrical power. So you can take the approach by finding power first, then divide it by time, or you could just plug it into the equation by saying energy is equal to IV times T. All right, so let's now work this out real quick. And so energy now is given as the current, which is 0.2. So it's going to be 0.2 multiplied by the voltage, which is 110, multiplied by time, which is 60 seconds, And so here we'll get 1,300 and what? 20 joules. All right, so that's now the answer there. Now for part B, let me go down to part B a little bit more. It says suggest 2 reasons why your answer in part A1 is less than your answer in part A2. All right, so let's go back up to part A2. So part A2 is 1,320 joules, but in part A1, the answer is 600 joules. But remember what the 600 joules is for the man lifting the crate through the vertical height of 3 meters. But now this will be the work done by the motors across the conveyor belt. So what is one reason now why this is different? Let's go back to the diagram a little bit to kind of show you what I'm getting at. So when you look at the height, which is 3 meters right here, right, compared to across the conveyor belt, which is this is the distance of a conveyor belt. So of course, going across a greater distance, naturally, it is more work done, okay, because the same force over a greater distance, it is more work done. And again, work is equal to force times distance. All right, so let's give some reasons right here why this is different, or the answer above is less. So one is that the vertical height is shorter. So first answer here is that the vertical height, okay, so the vertical height is shorter than the conveyor, let me take out of that, shorter than the conveyor distance, okay? All right, and let's even say, not even say conveyor, but the incline, because from an incline, right? It's shorter than the incline distance, which makes sense. All right, so it's shorter than that incline distance, shorter. All right, so again, let me show you one more time for you to get this relationship. Again, notice the distance again across the vertical height is only 3 meters. The conveyor distance here is 7 meters, which is much greater. All right. Okay, cool. Once you have that, then we are good to go. Now, some other reasons now why the distance or the energy is less when you lift across the vertical height, just lifting by the man directly rather than using a conveyor belt. Some other reasons right here could have been, one, you have a compensation for a number of things. You compensate for the following. So energy is compensated for, so let's put that there. Energy is compensating for, and compensating for a number of things right here. Compensating for heat loss, because heat will be lost by the motor as well. Not only that, but also friction, because you have to overcome friction by the conveyor belt. And also sound, if you think about it, because the motor will making sound, the conveyor belt may making sound, and also and all that type of energy. So there are a number of energy transferred or energy usage using the conveyor belt. So you have the heat loss, you have friction, you have the sound. All right. So those are generally the energy that you have to compensate for. So to lift the crate across that long distance, then you also have to compensate for these things. All right, so let's go to the next part of the question now real quick. And for part C of this question here, part C is a calculate the efficiency of the motor. So to calculate the efficiency of the motor real quick now. So the efficiency of the motor here is given as, let me give a quick formula. So the efficiency of the motor is given as the work output. Let's say work output. Okay. All right, so work output over the work input, multiply that by 100. So I'm going to say multiply by 100% right here. Okay, multiply 100%, all divided by the work input. All right, so what is the work output here? The work output is the work done in terms of the vertical height, and that is done by the man itself. So here now we can say that efficiency here, okay, let me say efficiency is equal to the 600 joules of energy that you have used by the man divided by that of the motor, which is 1,320. So if you go back to the part of the question right here, just to do it real quick, you'll see what I'm getting at. All right, so the energy that by the motor was 1,320. That of the man was 600 joules. Okay, so notice the energy right there, the two energy input by the man, but energy output, which is energy by lifting across the horizontal, the vertical height, and the energy input by the motor. All right, so once you have this now, we can now do all of this. Let's say this multiplied by 100% right here, times 100%, okay, then divided by 1,320. So this now will be equal to 45%. This is now 45%. All right, great. So the conveyor belt is 45% efficient. Now, part D now suggests one modification to the motor or the conveyor belt to ensure that the crate reaches the top floor in a shorter time. So what can you do to make this thing go faster? Now, one thing I wanted to point out that the power rating may be the same of the motor. That's not going to change, right? But what can you modify about it to make this done quicker? So what you're going to do here now about the motor, I'm going to tell you what you can do about the motor. I'm going to give you two answers, as a matter of fact. So if you're thinking about the motor modification, what you can do with this is to increase the current. You can increase the current, because remember now, if you increase the current of the motor, what will happen? The motor will turn faster, and a faster turning, the conveyor belt would move faster as well, right? So that's one modification to the motor itself. Increase the current input, okay? So increase current input. All right. And next thing you could do right here in terms of the conveyor belt. Okay, so let's think about the conveyor belt. So the conveyor belt, this is what you can do right now. What you can do with the conveyor belt is to lengthen the conveyor belt, okay? So we're going to lengthen the incline. Lengthen the conveyor belt is lengthening the incline just the same way, all right? Just to make a note of that. So you're going to lengthen the incline or the conveyor belt. So lengthen the incline, all right, and make it, and let me say, and make it less steep, and make it less steep. All right, so the less steeper it is the better it is. All right, I'm going to show a diagram just to illustrate this and let it less steep. All right, so there's a little demonstration I'm going to show you right now for you to understand what I'm saying, right? So the steeper incline is the more force you'd have to use to bring the object up the incline. So if you have, let's say this is a vertical height right here, right? And the incline is as steep as this. The distance is shorter. Yes, the distance is shorter going up the incline, but require more force, right? But if the vertical distance, a vertical height is that, and you lengthen the incline like that, it is less steep. And so it's less steep, you go up the incline gradually with a less force required, okay? And so you get to move faster again across the incline. Because think about going up a hill, for example. If the hill is really, really steep, you're going to take a lot of energy and a lot of time to climb that hill. But if the hill is just gradually increasing by small intervals, then you're going to realize it is way much easier to climb, okay? So this here will be a better model of an incline that you want to go up really fast. This model will not be effective or not be as efficient as the one on the right, simply because if it is too steep, then you may run into some problem by lifting the object, all right? So just to make a note of that, you increase the current, so the motor will move faster, all right? And hence it will carry the crate across the conveyor much faster. If the conveyor belt is lengthened or the incline is lengthened to make it less steep, also what's going to happen again, you're going to move over that gradual distance in a much shorter time, even though the distance is longer, because it requires less force, okay? So less force will be required, and of course less force, then definitely your power will be better. All right, let's go to question number 2. And question number 2 now, it says strontium-98 is a radioactive isotope that emits beta radiation with half-life of 50 years. So the half-life for this is 50 years. And two things here to point out. The time is 50 years and also emits beta radiation. So beta is given off. All right, great. Now we say give 2 reasons why this isotope is injected into the body instead of other isotopes for the long-term treatment of cancer. I notice a long-term treatment of cancer. So there are two main reasons in terms of the others. And let's think about beta and gamma, right? Beta, gamma, and also alpha. Now, alpha is the first one, right? So what about alpha that makes beta better? And because if you compare alpha and beta, beta is better to use in the body because beta is less ionizing. Okay, so I'm going to put it right here. So the first reason here is that the beta is less ionizing, all right, or of less ionizing power, all right, compared to alpha. Okay, so let's say compared to alpha particles, right? Yep, or alpha radiation. All right, so great. So that's one reason why I prefer use beta rather than alpha particles, because beta is less ionizing compared to the alpha particle. Another reason we compare the beta with the gamma, then beta has a less penetrating power. So therefore not go through all the structures of a body, neither will it emit into different regions of a body that you do not intend it to be, yeah? All right, so it is stopped by a couple sheets of paper. So here now, it has a relatively low penetrating power. Okay, it has a relatively low penetrating power. All right, and not only that, I'm going to give a next reason as well. Here, we could put a next reason right here, is that 50 days is just technically a month and a half, really, right? Compared to some particles that may live for a half-life of a couple thousands of years or a very long period of time. So the half-life is relatively short, okay? So it has a relatively, and I'm saying relatively because comparing to the others, right? It has a relatively short half-life. All right, so a relatively short half-life. Hence, over a long period of time, little to no residue will remain. All right, so you have no negative or harmful residue remaining. Okay. All right, just to make a note right there. So again, these are three reasons you can use that the beta is less ionizing compared to the alpha particle, and it has a relatively low penetrating power. Also, it has a relatively short half-life, and over a long period of time, there'll be little to no residue, all right, that will be left inside the body. Okay. All right, so great. So those are three possible answers there. All right, let's look at part B. It said radioactive isotopes such as the carbon-14 are used to date archaeological objects. This technique is called radiocarbon dating. Explain how carbon-14 is used to date archaeological materials. And so what I want to think about first and foremost, before I even start this, remember now, this method of dating is used for organic materials or for living structures or structures that was once living. During the lifetime of these living organisms, they will intake carbon substances, and also by nature they will also absorb some carbon-14 as well. And so while absorbing these carbon-14 once alive, they will be in their normal state. However, once that organism ceases to live, that means the time of death, there's no more intake of carbon-14. So what is in that body at that time will start to decay as regular, and then now we can use that carbon-14 that remain in the organism to now date. So let's put this in words real quick. All right, these are 2 marks, but let's put this in words as best as I possibly can, right? So how this is right now, I'm going to start by saying the remaining Okay, the remaining carbon 14, let's just say carbon 14 for short. All right, so the remaining carbon 14 in the material, okay, in the material is determined. So they're going to determine what is left in that organism or in that material is determined. Okay, so that's first thing to do is determine what is left. Okay, and so once you identify what is left now, what you're going to do now, you're going to do a cross check. Okay, so let's put it as a point right here. The remaining carbon 14 will be checked. All right, and that will be checked against now. That will be checked against the half-life. We'll check against the half-life, all right, of carbon. Okay, so we'll check against the half-life of carbon 14. All right, so whatever the half-life is, you're going to check it against that. And then now, and then you're going to calculate the time taken for that portion to be remain. Okay? And then the time taken for this portion to remain will be calculated. All right, so that's a step that will be taken there. So again, is about analyzing what is there, how long it takes to break down to that amount, and then you make a calculation. All right, so again, you determine what is left. All right, and once you determine what is left, you're going to check it against the half-life. So whatever the half-life is, you're going to use that half-life to calculate how long it takes for the carbon 14 to reach that point. All right, so okay, so great. Now for part C, all right, so now we say a Geiger-Muller tube connected to a counter can be used to detect and count nuclear reaction. A cross-section of the GM tube is shown in figure 2.1. All right, and so I'm going to quickly now outline a few things for you real quick right here. Before I even go into any question relating to this, I want you to notice something here. Now, the first thing I wanted to notice, right, is that there's a power supply that is connected to the GM tube. Now, the positive terminal of a power supply goes straight through. That means this central electrode right here is positive. I want you to make note of that. The central electrode is positive, and there's a reason I'm going to talk about that, because to understand how this thing works, you must understand that the internal electrode is positive. And then what I wanted to notice as well is that on the outer casing of this cylinder right here is negative. Okay, so there's negative going in. So this cylinder here is what? Negative. Okay. All right, so I want to understand that. So the inner part is positive and the outer part is what? Negative. And as a matter of fact, this chamber is closed and it contains a gas. And the gas is at low temperature as well. So I wanted to note that. Okay. So those are the three things I want to point out to you to understand how the GM tube works. Is the charges that are on the cylinder and the gas that is present within the cylinder. Is a closed cylinder. And then now from this, it is connected to what they call a counting circuit or a counter. Okay. All right. So let's go to the question now to see exactly how we're going to approach this and what they actually asked us. Is to explain how a GM tube works to detect nuclear radiation. So what I just said to you now going to help us to understand what is happening right here, what is taking place. So let's talk about them real quick. Now, first and foremost, right, is that the radioactive substance will enter the tube with the gas. The first thing you do is to pump the radioactive substance within this tube. First step, okay? So let's say that as one. We can number them. Let's say one. Radioactive. The radioactive substance enter the tube with the gas. Okay, with the gas. That's the first thing you want to make note of. All right. So once the radioactive substance enters the tube with the gas, there's something specific will happen here. Let's call this 2. Okay, so the second thing will happen here, which is very important. Let me scoop a little bit above the line so get this nice and easy. Okay, great. So this is part 2. And now what will happen here now is that when the substance react with the gas, so the radioactive substance, let me say radioactive. So the radioactive substance will react with the gas. Okay, so when that reaction takes place, now there's something specific will happen, right? Okay, we'll react the gas and electrons. No, make note of what I'm going to say right here now. Electrons now will flow out of the gas, right? All right, so electrons flow out of the gas. Okay. All right, so once the radioactive substance react with the gas, electrons will flow out of the gas. Now, what has happened here now? Think about it in this way. If electrons are pushing out of the gas, let's say E minus, right? If they're floating out of the gas within this chamber, all right, let's think about what will happen. What do you think will happen? Just think about it while I finish writing these negative electrons right here. Electrons are negatively charged. So think about what will happen by all means of logics. Now, around the casing of the tube is negative. So the only thing will happen to these negative electrons, they attract to the positive electrode or the central electrode, which is positively charged. So they're going to be attracted now to the positive electrode, and they're going to hit that positive electrode. The rate at which they hit that positive electrode will be read by the counter. Okay, so let's just complete this now. So okay, so you see what is happening here now, because electrons will start to move rapidly and hitting that positive electrode. The hitting or the rate at which these electrons knock onto that positive electrode, attracted to that electrode, will be read as the count rate. Okay. All right, so let's put a next step right here, because access is at 3 marks, but 3 marks. I'm gonna give it like two more points to make this understandable. So 3. The third point I want to say right here now, that the electrons are attracted to electrons attract to the central electrode, to the central electrode. All right, so that's the next step. So the electrons will be attracted to the central electrode, right? The electrons will be attracted to the central electrode, right? And then the fourth thing now that I want to talk about right here, to make it for you to understand what will happen here, is that the rate at which the electrons are attracted to let me go a little bit more. So the rate at which electrons are attracted to the electrodes, all right, so the rate at which the electrons are attracted to the central electrodes are counted as the count rate. Okay, this is the next page. I must go back a little bit more here, and let's put the extra piece right here. All right, so the rate at which the electrons, and put an S right there. All right, electrons are attracted to the electrodes. All right, they are counted as the count rate. And put that last piece right here. All right, attracted to the central electrodes. Is counted as the count rate. All right, so it's all about the positive central electrode, and also negative electrons attracting to it, and the rate at which they attract to it will be picked up by the sensor as the count rate. All right, so let's go to part D now. And for part D, said 4 nuclides are shown, which is I131 and 5,3, and then you have 218 radon, and then we have xenon, and then we have radium. All right, so here now, this is iodine, matter of fact. All right, so now it asks us right here, say on the symbol, it's one of the symbols represent the parent nuclei. So this is very important now. So one of these now represent the what? The parent nuclide. So I'm going to just highlight this real quick. So one of them indicate the parent nuclide for alpha decay. So we're talking about the alpha decay right here to another of the nuclide in the list. So therefore now, if one is a parent, then one must be a daughter. Okay, nuclide. So in other words, one come from the other one. When emit by a alpha decay, that's going to be very important. It's to give the symbol for this parent nuclide. Before you go into this, and for understanding purpose, I want to understand this. When something emits alpha particle, it therefore means it gives off a mass number of 4, right? And a proton number of 2. So we're going to use this now as our base to find out which of them, right, will lose 4 and 2 to give another one. So we know for sure that the 131 cannot be any of the answer. Why? Because they can lose 4 mass number to give some that is greater than itself. If they lose it, it must be less than itself. So 131 and 131 cannot be the answer. Okay, they could not be. Okay, because for the mere fact to emit the alpha particle, it therefore means you're losing a mass number of 4. So we can check to see which of these two, now, which is 218 or 222, which of them, when they lose 4, will give us another number. All right. So if 218 loses 4, will it give 131? Because it can't give 222, and that is not correct, right? If you lose 4 here, what you're going to get here is 214. So this is not correct as well. So the only other option right here now is 222. 4 from 222, what you'll get is 218 actually, yes? So we know that our parent nuclide must be 222.88, okay? All right, so let's go do that really quick. All right, so a parent that they're looking for here going to be, that's radon, that's RA. Okay, so RA, and it's going to be 222 up top here as a mass number. Okay, 222 and 88 as a proton number. All right. So again, you know, it's always about what you're losing. All right. So always think about what you're losing right here. Again, alpha, you lose 4 and you lose 2. All right. So great. So that will be your parent molecule, right? In the next part of the question, it said, write out the decay equation representing the decay of the parent nuclide mentioned in D1. So what you're going to do here now is to write the equation here by putting your parent first. So let's put the parent right here first. All right, and so the parent going to be RA, and the RA, which is 222 as the mass number, right? So put 222 there, all right, as the mass number, and then 88 as the proton number. All right, and this now will decay into, we're sure about one molecule, so we're sure about the alpha. So now we're going to emit the alpha, and alpha is 4, right, and 2. And it's going to give you another nuclide, and the nuclide is going to be here. Let's not even sure about the nuclide yet, but if you, whatever you're going to add right here must equal to 222. So again, 4 from 222, we're going to get what? 218. All right. We're going to get 218 right here. 218. Okay. And you're going to minus 2 from 88. You're going to get 86. So let's go back to our thing and see which one of them match up to 218 and 86. Okay. So let's say 218. All right. So 218 and 86. This will be our nuclide that is formed. It is Rn. All right, so it's going to be this. All right, so that will be the equation right there. All right, great. So again, the total mass on the product side must equal to total mass on the reactant side. All right. So if alpha particle was absorbed, then you put alpha particle on this side, but it's emitted, so it's on the product side. So emit means to give off, to absorb means to take in. So those are words that you look out for when it comes on to radioactive questions. All right. Now let's go to the next part of the question right here now. But it's part 3. It's a from one of the nuclides shown, name the daughter nuclide which could be produced by the emission of a beta particle. So what do you want to look for? A beta particle. A beta particle, there's no mass, right? There's no mass given off. So the first thing to know about beta particle, let's just write that down real quick. So a beta particle will be this, 0 mass, right, and a -1 proton. All right. So what I want to point out right here now is that if this is going to emit a beta particle, right, a beta emission, then what you must understand is that the mass will not change. The mass will not change, but the proton number will increase by 1. So let's look at the two things now that make this possible. All right. And so the ask us though is that from a nuclei shown, name the daughter nuclei. We're naming only the daughter nuclei, not the parent, but we need to know what the parent is, right? So what I could do is to show you the reaction. Let's go back up here real quick. So the two nuclides with the same mass number is 131 and 131. All right. But emitting a beta particle, which means the mass number will increase. So this here will be the daughter coming from the parent. The parent is iodine. All right. So if this is a parent, because remember now, by emitting a beta particle, the proton number increases by 1. So we know that this has to be the daughter. So what I could show you the reaction below here to show you exactly how we get it. All right, and then I talk about the answer. But remember the answer now, again, will be this. And matter of fact, let me show you something, because this question said name. Yeah, it said name it. Not to write the symbol, but it said name it. So I'm going to show you name this. But let's do the equation first, then I name it. Now again, we're going to move from 131, which is iodine, right? All right, let's put this right here. And then now the proton number was 53. And it will give off the beta particle. And the beta particle that was given off here, again, the mass number is 0 and a -1 proton, right? And so whatever we can add to this, again, there's 0, the mass doesn't change, it's going to be 131, right? And the particle given here now, the atomic number or the proton number must increase by 1, so it's going to be 4, okay? And so definitely we know this here is xenon, okay, which is this. And so if you look at it, right, a -1 plus 54 will give you 53. 0 plus 30, but plus 131 will give you 131. So our answer right here, I'm going to show you to name this. You can either do it one of two ways. You can say, use name by symbols, or you could actually, let me see, I'm getting, okay, great. So what you can do, you can use the symbol first by saying ZE, which is for xenon, and they put the mass number. So that's how you name the isotope, which is 131. Or you could actually write out the name. Right, you can actually write out the name, which is xenon, all right, and then you put the symbol, the mass number there, which is 131. So either way is acceptable, all right. But it said name the daughter nuclide, not to draw the structure or the symbol, because the symbol will contain two things: the mass number and also the proton number, right? All right. So there we finish with that question. We'll jump on to the next question. This is question number 3. All right, and again, I'm just really strapped for time. I hope when I'm finished this, I could do part B. All right, but we saw that work out. All right, so for question number 3, it said this equation is about work, energy, and power. It's a figure 3.1 shows a man pushing a cart with a constant force of 26 newtons at an angle of 50 degrees. So to understand this question, let's do something here real quick, right? I'm going to draw this in terms of a vector diagram. So the man is pushing across a horizontal ground, is pushing with a force, and they said that the angle that is pushing with is 50 degrees, right? So here is 50 degrees, just to make a note real quick. So 50 degrees right here, right? And he's pushing across here now with a force of 26 newtons. So the 26 is going in that direction, right? All right, and then I could just broken line this vertical lift, because this would be the lift from the ground up. All right, so this is what is happening here. That's what the man is actually lifting, right? So that's a vector diagram representing what is taking place right here. As a matter of fact, we can call the horizontal distance x, and we can call the vertical height y, okay? All right, so now we have that as a vector diagram. Now look at the question. Where is a calculate the horizontal component of the force exerted by the man pushing the cart. So how much force is he pushing this way? Okay. And just to make a note of that, all right, because it's going this way. So I'll put just our head to show exactly where it's going. All right. All right, so great. Now, once we establish that, now we want to figure out now the horizontal force. So to find the horizontal force, let me show you the diagram in the same time, right, while I calculate this. So what I want to do now, we have x, we want to find x. So x here is the adjacent side to the angle, okay? So adjacent now over hypotenuse is given off cos the angle. So cos the angle is the adjacent over the hypotenuse. So what you can see right here now is that cos the angle, which is cos 50, right, is equal to, so cos 50 is equal to x, which is the horizontal, divided by the hypotenuse, which is 26, right? So in other words, now we can also state that x then is equal to cos 50, right? Cos 50 times 26, all right? And so by that now we can simply say, let's go on a little bit more. You don't need the diagram anymore. There's no need for a diagram anymore. So we can say now x is equal to 0. So cos 50 is 0.64 multiplied by 26, and that now will give us 16.64. Okay, give us 16.64, and this is Newton because this is in force. Okay, so 16.64 newtons. All right, so great. Now let's jump to the next part of the question. Now it said the man pushes the cart at a distance of 5 meters along a horizontal surface. Calculate the work done by the man in pushing the cart. So you push a cart here now for 5 meters along the horizontal, and the horizontal force is 16.64. So you're going to use this force to push a cart or the wheelbarrow across a 5 meters. So now we're going to calculate the work done by doing that. And so the work done by doing that, remember what work is? Work is equal to force times what? Distance. And so therefore the work now is equal to force, which is 16.64 multiplied that by the distance. Then the distance here is 5 meters. And so this is equal to 83.2 joules. Okay, so that's the work done by going across the horizontal distance. Number part 3. It said there is a constant horizontal frictional force of 16 newtons acting on the wheels of the cart. Calculate the magnitude and direction of the resultant force. Now, I'm going to show the calculate the magnitude, which is the size, and then I talk about the direction after that. I'm going to use a diagram to determine the direction, all right? Okay, so now let's look at this in this way. Friction, the frictional force is opposing the horizontal force. So let's go back to our horizontal force. So horizontal force is 16.64 Newton, right? So I'm going to show you something real quick. If the horizontal force is going oppositely to the frictional force, which is 6 Newton, therefore we can say 16.64 minus that 6 Newton because they're going in opposite direction. So of course they will cancel, the 6 Newton will cancel a portion of that horizontal force, would leave us with now 10.64 newtons. Okay, it's 10.64 newtons. Now let's talk about the direction now, because direction now is no critical. Let's go back to the diagram to figure out where this is going, because we know the man is going forward, right? But what I want to do is use a vector diagram to see if we could really understand this. So let's draw this in terms of vector. All right, let's go up, let's go down. All right, we all know that up here will be north, down here will be south. Okay, so this is the south, and so we're going to straight across here on a horizontal plane, and so this is the west, and this is the east. Okay, so now we establish these coordinates. Now let's think about where is he pushing the wheelbarrow. All right, again, I just want to be very, very specific in terms of my direction. Right, so let's use blue for this. Now the wheelbarrow is going here, through here, yeah? So what direction is he going? Really, is going into a southwestern direction, right? Okay, so that's where E is heading. All right. Typically, I know you don't want to say it's going west, but it's not going exact west if you draw coordinates, right? It's going actually southwest. All right, so going a southwestern direction. All right, so let's just quickly put that. So the magnitude of the force again, when you take away friction from it, is 10.6 4 newtons, but is traveling in a what? Southwest direction. So southwest. All right. Okay, so the force that is pushing with, we go in the southwestern direction. And the value of that is 10.64. And the 10.64 is the magnitude. All right, so part B of this question now, we said if the cart's mass is 20 kilogram and is lifted by the man onto a ledge of 1.2 meters high, determine the gain in potential energy of the cart if gravity is 9.81. And so to calculate the potential energy gain right here, potential energy, right, is equal to mass times gravity times height, yeah? And so the mass given here, so let's just say potential energy here now, is equal to the mass, which is 20 kilograms, multiplied by the gravity, which is 9.81, all right, then multiply that now by 1.2, which is the distance or the height. And so here now what we'll get at this value, so 20 multiplied by 9.81 multiplied by 1.2, you get 235.44 joules. All right, so great. Now let's go to the next part of the question now for this. And next part of the question said the cart accidentally falls 1.2 meters vertically from the ledge to the ground. So it falls the entire height. Is to calculate the cart's velocity just before it hits the ground. Neglect drag. Now, the most important thing you need to figure out right here now, remember now, as the cart is falling, it is converting from potential energy into kinetic energy, right? So when it just hit the ground, or just before it hit the ground, all the potential energy will be converted to kinetic energy. So what I wanted to understand right here now, at that point, the kinetic energy is equal to 235.44. Okay? So this is potential energy, but just for it hit the ground, the kinetic energy, let me just write that right here. The kinetic energy, okay, the kinetic energy is equal to the loss in potential energy, which is going to be 235.44. All right? So there's a total conversion from potential to kinetic. That's the first thing you need to establish. Now, once you establish that, what you need to think about next now is how to calculate velocity. Now, from this formula, from kinetic energy is equal to half mass times velocity squared. Okay, let me just put that in with my pen. Okay, so it's equal to half mass times velocity squared. All right, so once we have that now, we can now find what our velocity is. All right, let me do the rest with the pen to make it go a little bit faster. All right, and so here now we can simply say that let's find v squared. So v squared, okay, will equal to, right, the kinetic energy, right, all divided by half of the mass. Okay, half of the mass. So now what we can say, we already have kinetic energy. So we just plug in the formula. We have the mass, which was the mass, what was the mass again? That was 20, yeah? Let me just go back up. The mass was, 20 kilograms, right? So the mass is 20 kilograms. Let's just go straight into it and put our stuff in. So what you can see here, let me put a line across there. So what you can see now is that v squared, which is velocity squared, is equal to 235.44, yeah, divided by half the mass, and half the mass is 10. Okay, half the mass is 10. So what we can simply say now to find v now, v is equal to square root of, all right, so remember now, if you divide by 10, you're going to get 23.5, right? So we're going to say the square root of 23.544. Okay, and so our velocity right here now is equal to the square root of that. You're going to give us 4.85. All right, so going to be 4.85 meters per second. All right. All right, so great. Now that is completed right there. All right, good. All right, so now we're going to jump on to the next question real quick, right? And I'm running out of time. And so I'm going to go on to question number 4. All right, so we're going to stop right here for today with this question. So let's run through it real quick. All right, so this question now is about electrical circuits. It's a figure 4.1 shows a low voltage circuit, right? So low voltage means that you don't have enough voltage to supply all the equipments, right? So something not going to work properly. So right here now it said, so matter of fact, let's analyze it. So we have 3 bulbs, X, Y, and Z. We have a volt supply or DC supply of 12 volts. So that's the only thing we know so far. And of course, the circuit is in parallel. Now here said now on figure 4.1, indicate with the circuit symbol a point in the circuit where a switch could be placed that could turn off lamp Y and Z at the same time, but would leave lamp X still lit. So I want to turn off Y and Z and leave X still lit. So where would you put that switch? The switch should not affect X at all. So what you could do as a circuit symbol, you could put it right here. All right, and this is the switch symbol. So you make the switch symbol right here. All right, so that would be the switch symbol right there on that side. A matter of fact, you could put it on this side as well if you do desire. So when you put this yellow line, you could put it right there as well. So either here or here will turn off the current flowing to Y and Z at the same time. If you want to turn off Y, you put the switch right on this line that I'm pointing to right now, or this line right here. If you want to turn off Z by itself, you put the switch right here, or the switch right here. Okay, but either side is good. Now the next part of the question, let's go into that real quick. Is state now on the figure 4.1, mark with the letter R. No, I think I need to go back to this one. Right. Part B. It said draw the circuit symbol for a component that would vary the brightness of lamp X. So what can you use to vary the brightness of lamp X is to put a variable resistor there. And remember, the resistor will determine the amount of current flowing. So you put a variable resistor, you could always change the value. So it's going to be like that. All right, so that's a symbol for a variable resistor. Or you could use this symbol as well. All right, so either. All right, so great. So that's a variable resistor. So a variable resistor will change the amount of current going towards the lamp. So that will be the correct drawing or the correct answer right there. So for part 2 now, it's on figure 4.1, mark with the letter R where this component could be placed. So where could you place this variable resistor? We're going to label that R. So to put it, let it affect only X alone, it either be right here, then I'll put R right here. So it's going to be R, going to be right there, or it could be right here as well. Right? You do not want to put it on the outside, because putting it on the outside will also affect Y and Z. So it must be on these internal connection that going directly to X. So only correction going directly to X. So on that side or on this side, doesn't matter which side I put it on. All right, it will affect the current flowing towards X. All right. However, though, if you're doing a real circuit, you want to put it on the positive side, but there's no indication to say which side is positive or negative. But if it was a circuit showing positive and negative, you always want to put your switch and the resistors on your positive side. Okay, and simply because of conventional current. All right, conventional current. All right, so let's go to part C now. It said the current in lamp Z is 3 amperes. Calculate the resistance of this lamp. Okay, so first thing I'm going to do right here now is think about the amount of, let me give you the formula first before even going to that. So formula you're going to use here is V is equal to I times R, right? Okay, you want to find resistance. You already have current. All right, so you know what voltage is. Let's go back to the voltage. The voltage in the circuit, as I remember, it is 12, right? Yeah, so it's 12 volts in the circuit. So we're going to calculate now R. So R now from this formula, we can say R is equal to V over I. Okay, so V divided by I, which is voltage divided by current. And right here now we can say that the resistor is equal to the voltage, which is 12 volts, divided by 3, which give us 4 ohms. All right, let me try to draw the symbol here for the ohms. All right, okay, all right, that's not bad. All right, great. All right, so that will be the resistor or the resistance value for lamp Z. All right, so for part D now, it said the lamp Y is removed. You take out lamp Y, explain why lamp X and Z still work normally. All right, so it's a parallel circuit to start with, right? It's a parallel circuit to start with. So you take out lamp Y, right? You take this one out, don't need it anymore, gone, gone, gone. X and Z still works. But if you notice it, current gonna flow still, no matter what, right? So let me give you the answers here now in words. It's a parallel circuit to start with, right? It's a parallel circuit. And parallel circuit, each component has their own what? Path to current to flow. So I'm gonna make a note right here now. So each lamp, right, has a separate path for current to flow. Okay, that's the most important thing. All right, and so then therefore now each, and we'll make sure add on this piece to it. Each path, right? Each path is directly linked to the power supply. Okay, is directly linked to the voltage supply. All right, so they are directly linked to it. All right, so each of them have their own path of current to flow. So take out one lamp will not affect the others, right? And simply because it's a parallel circuit. All right, and in parallel circuit, there are more than one pathways for current to flow. Let's look at part 2 right here now. And for part 2, it said the current in lamp X is 1 amp. Calculate the current supply by the battery when lamp Y is removed. So we already know the current for lamp X, which is 1 ampere. But let's go for lamp Z now. We calculate that up top. So the current, the current here for lamp Z is actually 3 amperes. We didn't calculate it. They actually stated. So if lamp Z is 3 amps and lamp X is 1 amp, then the total amperage coming from the battery will be the sum of those, because remember now, the current in a parallel circuit, the total current in a parallel circuit is equal to current 1 plus current 2. So therefore, total current, let us say IT right here, total current is equal to the 3 amperes plus the 1 amp, which give us 4 amps right here. Okay, so it's a total right here. All right, so great, this is it. All right, so this is where we end for right now. I'm going to try my very best to see if I could do section B. All right, if not, then I'll do it another time. All right, or for future reference. All right, so for now, do well, keep safe.